Welcome to this review session for the Chem2A Exam 1 coming up about a week from now. This is going to cover chapters 1 through 3 for the 4th, 5th, and 6th editions, and just chapters 1 and 2 of the 7th edition. So if you're a 7th edition user, don't do that chapter 3 because we're not going to cover it before the test. So here we go. I try to do these review sessions for every exam. I don't make any promises, but I think I've got enough time to do this one. So let's see how far we can get on this. This is going to be a two-part review. This is just the first part that covers measurements and physical properties and sig figs and that kind of stuff. And part 2 is going to cover atomic theory, electron configurations, that kind of business. All right, so just as a review, let's review chemical and physical properties. Chemical properties, this is the tough one. So if I say properties or changes means the same thing. It involves changes to the fundamental structure of the compound. That's the key statement, is something's going to happen to the bonds in the compound from the reactant side of a reaction to the product side. And a compound, by the way, as just a reminder, a compound is comprised of two or more elements joined together by bonds. Okay, so those bonds, they got to change in some way for a chemical change or physical property. Now, examples, there's plenty of examples. Combustion, anytime you burn gasoline, you take gasoline, which is one type of, several different types of molecules, and they get converted into carbon dioxide and water vapor. They come out the tailpipe. That's a chemical change because the bonds change, literally. Rusting, you leave your iron bicycle out on the alleyway and it rains, it's going to rust. So that's a chemical change. The iron reacts with oxygen, produces iron oxide. Toxicity, so toxicity, you ingest something that's toxic, it's going to be messing with your chemicals and it's going to do some chemistry that you probably don't want. Toxicity is definitely a chemical property or change. Tarnishing, silverware tarnishes. That's kind of the same thing as rusting, although it doesn't involve iron. It involves things like silver. Now, physical properties, this one's an easier one to understand. So this is something that does not involve a change to the fundamental structure of compounds. So things like color, melting point, boiling point, evaporation, conductivity, luster, all kinds of examples like this. Odors, even another one. So that doesn't involve any changes. Even evaporation, so when a puddle of water evaporates into a gas, nothing happens to the water molecule itself. It just changes phase, as we say. It starts as a liquid, becomes a gas. Nothing changes to the chemical makeup of a water molecule. It starts as H2O, ends up as H2O by the time it's done evaporating. Okay, so that's chemical and physical properties. And a lot of the time, by the way, too, it can be both. And I usually have that option on exams where you can say, no, it's both. It's both a chemical change and a physical change. That's fair. So just a couple of sample questions with respect to, well, here's what we're going to do. We're going to classify these things as chemical or physical changes. And I just got done telling you that iron rusts. So this first one, if we're going to call this, let's just do a real extreme shortcut here and just say that physical, I'm going to circle with a P, and chemical, I'm going to circle with a C. So when we come to iron rust, actually, let's do this too. Let's say both. It's both a physical change and a chemical change. Arguably, iron rust is both because it changes color. You see that iron change from a normal metal color to something that looks pretty reddish. That's a physical change, but it's also doing some chemistry to do that, so it's both. Sulfur is yellow. That's typically or purely a physical property, so its color is just physical. Nothing changes about the sulfur itself. Boiling point of ethanol is 78. That's a physical property only. So when you boil something, you're not changing the chemical makeup of that substance in any way. You're just boiling it. You're converting it from a liquid to a gas, but nothing changes about the bonds. Arsenic is toxic. That's a chemical property. So something's happened to your molecules in your body when you get poisoned by something. Silverware tarnishes, that's a chemical process, although you could argue that's maybe both because you might see some color changes too associated with that, but that's chemical. Cement hardens, this is a tricky one. So cement hardening, I can tell you right now, is a chemical change, but also you can consider it a physical change, so we're going to call this both. But that hardening process is chemistry that's happening. Copper conducts heat, that's purely physical. Okay, so nothing changes about the copper metal itself when you pass heat through it. Gold conducts, also just purely physical. Nothing changes about the chemical makeup of gold. And then finally, a puddle of water evaporates. This is the tricky one, but it's only physical. Nothing happens to the water molecules when they evaporate from the liquid phase to the gas phase. Nothing changes. Okay, so that's the difference between chemical and physical changes. Just a couple of quick examples. By the way, this review is not going to be all-encompassing, so everything I talked about in the lecture is not necessarily going to be in this review session, so keep that in mind, be forewarned. But the golden rule is if we talked about it in lecture, it's fair game for the test. I'm just going to take you through the most difficult things and the things that we need to practice before the exam. All right, so let's go ahead and clear the screen here and just say a few more things, then we're going to look at some more examples. So classification of matter, there's 4 ways you can classify matter, and again, some of these things are a little bit tricky, but I think one little category that's pretty easy is pure elements. And so if you're talking about a substance, it could be a pure element, and if you can find it in the periodic table in any way, then we call it a pure element. For example, copper, gold, phosphorus, oxygen, even oxygen. It might be tempting to say that oxygen is something else, but actually, even though it's an O2 molecule, it's called a diatomic molecule, it's still one element type, and that's the key thing when it comes to pure elements. It has to be a single element type, not mixed with anything, and no different elements combined to make this. As different than pure chemical compounds, so kind of similar but different, here we're talking about 2 or more different elements that are bonded together or combined, not mixed with any other molecule type or compound type. Baking soda. So if I get out some baking soda, that's purely sodium hydrogen carbonate is the name of this compound, and there's nothing mixed in with this sodium hydrogen carbonate, okay? But it is 2 or more different elements that are combined to make this compound. Same goes for table salt. Table salt is sodium chloride, and this is not a pure element because we've combined 2 different elements together, but we assume that it's not mixed with anything else. Teflon is a complicated molecule. It's a polymer. I don't want to get into the structure, but I can tell you that it's a pure chemical compound. It combines carbon with fluorine to make a polymer, but it's just that substance, that Teflon coating. Table sugar is also known as sucrose. So it's got 12 carbons, 22 hydrogens, 11 oxygens combined together, bonded together, and that makes up that molecule. It's not mixed with anything else. We hope it's not mixed with anything else. So that's pure elements, pure chemical compounds. They fall under the umbrella of pure substances. Now, the other type is mixtures. We can have heterogeneous mixture, and that's one easy one to spot because we know it's a mixture, whatever it may be, like granite rock. In granite rock, we can see the individual speckles, and those speckles are different minerals that make up the granite rock. So that's clearly several different compound types mixed together, but we can still see the components. Dirty water is kind of a stupid one, but I can pretend I'm a kid again and take some dirt, mix it in with water, make some mud. But clearly you see the water component, you see the dirt, and because I can see the components, it's a mixture. So 2 different things that are mixed together, I can see the components. This is a gimme. So oatmeal raisin cookies, of course, we're talking about cookies with raisins in them, so you can see the individual components, heterogeneous mixture. Now, homogeneous mixtures are mixtures, but I can't see the individual components of the mixture. So that would be something like milk or black coffee or salty water. Salty water is a good one. So we can't see the sodium chloride that's dissolved in the water, but nonetheless it's there. So it's a mixture of 2 different compounds uniformly mixed together. We can't see the components. Same goes for sugar. I can dissolve sugar into hot water, no problem. I can't see the individual sugar grains once it's dissolved, okay? So 4 ways we can classify matter. One type is pure substances. That can be a pure element, pure chemical compound. Another thing is mixtures. It could be heterogeneous. It could be homogeneous. I showed you this picture of the periodic table. We're going to be jumping around a little bit. Remember, this is a review session. So the periodic table, one way you can organize the periodic table is by metals, metalloids, and nonmetals. If you had to guess, most of the table is comprised of metals, so that's the lower left part of the table. So down here, but also lower left. Nonmetals are fairly easy to spot. They're the upper right-hand corner. The hardest ones to spot are these metalloids, and they're generally going to hug this black zigzag line that goes down from the upper left down to the lower right, and anything that essentially touches this black zigzag line, except for aluminum and except for polonium, is going to be considered a metalloid. Metalloids are also known as semimetals, too. They're the same thing. Metalloids, semimetals, same exact thing, by the way. Hydrogen, by the way, too, is in kind of a funny spot, and that's also considered a nonmetal. Keep in mind. Now let's talk about measurements. Let me just back up. Nope, I didn't skip a slide. So let's talk about measurements. Measurements are comprised of a value and a unit. So I measured the length of a paper clip or something like that. The value is, whatever, 2 centimeters, and the unit is the centimeter part. Now, on tests, I frequently do this. I'll make you do measurements. I usually draw pictures of thermometers, rulers, that kind of stuff. And I want to make sure that you are measuring things with the correct number of sig figs. It's all about the sig figs. We may disagree about a digit or two because of the estimation of the last digit, but nonetheless, we should all agree in terms of how many sig figs a measurement should have. And of course, once we start doing calculations with measurements, then we have to round numbers properly too. Now, I've got a short little video coming up in just a second where I'm going to take you some of the common measurements that we've already seen in the laboratory. For the most part, I suppose you could skip over the video part of it and just jump right to the calculations, but I'm going to show you how I made these measurements and what to look for. And then later in the presentation, like I already said, these measured values that I'm about to measure in this video, I'm going to use those to calculate the density of a small nail. I just grabbed a nail from my garage, and I've got a grad cylinder, I've got a balance and all this kind of stuff. So I'm going to show you how to make measurements. You wouldn't think that there's too much to say about measurements, but you really have to be careful when you look at measuring devices. You have to really figure out how many sig figs you're going to get from the measuring device because it varies. Now, the balances in our laboratory typically give the most sig figs. You just read the value. Triple beam balances, too, you got to do a little more work because they're not digital, but nonetheless, they're still fairly accurate. You can get a lot of digits. Now, something like an Erlenmeyer flask with those graduations, those are not very accurate because you can only usually get to the nearest milliliter if you're lucky. Volumetric pipette, that's better. You can get to 4 total digits of sig figs. Okay, so you just got to look at the measuring device and figure out what the graduations are worth, and you got to figure out how many sig figs you should get. So take a look at this video, and then later I'm going to do some calculations with the measurements. Hello, in this little tutorial I'm going to show you how to measure the density of a nail. We're going to get a chance to work through all the measurements that we've seen in this class so far, including length measurements, volume, temperature, and mass. So of course, to get the density of this little iron nail, we're going to need 2 measurements. One is going to be the mass, of course. I got my little home scale here. And secondly, I'm going to need the volume. Now I'm going to show you 2 ways to get the volume. One way is going to be we're going to take some measurements using some calipers and a ruler, and we're going to calculate the volume based on those measurements. And secondly, we're going to do it the easier way with a graduated cylinder. So first things first, let's look at the mass. So I've got my home scale here. I'm going to turn it on, and luckily for me, my home scale tears automatically. So as soon as I turn it on, tear means that the scale sets to 0 for me. And then with the nail on it, if you can see this, is the scale is saying 2 grams at this point. Okay, so 2 grams, and it's dancing around already. Unfortunately, this is just a food scale, so it doesn't really get us to the nearest milligram like our classroom scales do, and that's going to be the real bummer about this experiment. But of course, you see this triple beam balance. Actually, this is more than triple beam balance. I can, of course, try to use this one, but sadly, this thing is broken. I've got this as just a decoration of my house. This is how nerds decorate their houses, with balances. And if this did work, what I would do normally, of course, is just move all these little sliders, these weights, over to the left, put my little object in there, and then try to balance it out. And of course, I would predict, based on what my food balance said, is I'd try 2, and then I'd slide this little scale thing over and just read this as carefully as I can. Now with this balance, I can get down to, as I look at the scale, I'm looking at it right now, I can definitely get down to the nearest 1/10 of a gram. I can get down to the nearest hundredths. And by estimating the 3rd digit, I can definitely get down to the 1/1000th of a gram for this balance. That's if it worked. Unfortunately, like I said, we're going to have to stick with the kitchen scale. That's the best I can do. Now, what about the measurements of the nail? So I'm going to retrieve this off of the balance. And one thing that I'm going to have to get for sure, of course, is the length of the nail. So I've got a little Shasta College ruler. Not only am I going to have to get the length, but this is a weird shaped nail such that the head has got a little cylinder shape. The shaft of the nail is just a cylinder, and then the tip is more like a cone shape. So by taking careful measurements of the length and the diameter of the circle, and then the diameter of the cone, I should be able to get this. Now the ruler is going to get me only so far, so I've got this little caliper here that, fortunately for me, I bought this as a centimeter reading, and I don't have to convert to inches, from inches to centimeters later. So this is something I bought for woodworking, but it's coming in handy right now. Okay, so that's kind of the hard way to measure the volume. The easy way, of course, is something we talked about in class. The easy way is just to use a graduated cylinder, of course. And so I've got one from school here. Normally what we would do, and we did this already in the laboratory, is I'd fill this half full of water. I'd take the initial volume of water, which is, you can get this one down to the nearest, let's see, you can get this down to the nearest 1/100th of a milliliter pretty easily in this grass cylinder, so that should be no problem for this. Okay, so the initial volume of water, then what would happen is I'd drop the nail in carefully and I'd take the final volume of the water. Of course, this is a water displacement measurement, and this is really the most accurate way to do it because the nail's got a weird shape to it, of course. So that's two different ways to get the volume, and we'll do that eventually. Now, the last thing that I have here, of course, is a thermometer, and before I'm done for the day, I'm going to measure not only the density of the nail, but I'm going to go on to measure the specific gravity. And for that, I'm going to need to measure the temperature of the water. As I look at this thermometer, it's going to be accurate to the nearest, easily to the nearest 1/10 of a degree Celsius. And I'll get a chance to do that. So of course, to calculate the specific gravity, we assume that the nail temperature is the same temperature as the water. So I'll do a quick calculation. I'll show you how to do that. All right, so this is just the introduction to the measurements that I'm going to be making on the nail. Of course, I'm going to get more accurate measurements. I really didn't spend the time that I need to. I've got my little macro camera set up, and I'm going to show you really detailed pictures of what this looks like in terms of the measurements. Not so much for the mass, of course, because my scale doesn't work. I'll just show you that, you know, it's 2 grams as best as we can do. I may have to make up a value in that case. I'll show you the graduate cylinder, how to read that properly, the calipers, the ruler, and lastly the thermometer, and then we'll do some calculations on the computer. I've got the graduated cylinder all positioned, ready to go, and it's got a little bit of water in there. I'm going to go ahead and take a picture with my lens to see what the initial volume of water is. Let's take a look. So I'm going to take a few images just in case one of them is blurry. Okay, so now I got the nail again. So here's my nail. This is the best way to get the volume of that nail. I'm gonna drop it in. Try not to splash outside the water. Whew. I got lucky. It looks like it's okay. I'm gonna refocus the camera here again and take another image. I'm gonna take 2 images just in case. Without a doubt, this is the best way to get the volume of that nail. It's really going to be tough to take measurements, but we're going to try it that way as well. But this is water displacement. This is one way we had to measure the initial volume of the water, the final volume of the water, and the difference in volume is going to be due to the nail itself. Now we're going to pretend for a second that we actually have a working balance here. It doesn't work. I've already explained this earlier, but this is a triple beam balance. And I've just put the nail in there, and the idea is to slide these weights over until the arm balances out with the 0 there. So just a pretend measurement for a second. I'm going to slide these things, focus the camera, take a picture, and then later I'm going to check this value, but I'll take another image before we go here. Okay, so let's see. Can we see the slider? We can. And again, this is just a fake measurement, but I'll show you how to read this properly to the right number of significant figures when we get ready to do this. All right, I've got my camera positioned above a ruler and the nail. So what I'm attempting to do is just to simply measure the length of the nail for now. And I've just got it head to the tip, and I'm going to go ahead and take a picture. I think I've got everything ready to go. I'm going to focus real quick and snap a picture and see how it turns out later. Let's just take 2 pictures for good measure. Now the ruler is just measuring the total length of this, and what I really need to do is also measure the tip. So I'm going to go ahead and just spend a second or two taking a picture of that as well, as best as I can. I can only do so much with the ruler, so I'm not expecting this to turn out very well, but we'll see what we can do. Okay, one more image. And then lastly, I'm going to stand it on its head, because ultimately the head of the nail, I'm going to have to measure the diameter of that, and I don't think this nail is going to cooperate, and I can see why already, because it's got a slightly rounded head, so I'm definitely going to have to use my calipers to do this and not the ruler. So we'll do that in just a second, but for now, here's some ruler measurements. We're making progress here on our approach to measuring the volume of the nail using measurements like length instead of volume displacement with the water. So I've got my nail in a more precise instrument here. These are calipers, and I've got the nail positioned head to tail, and so I'm measuring the length, and it looks like it's about 50 something or other. I'm going to go ahead and take a picture. I'm going to take a couple of pictures just to make sure I record this and can find it later. Okay, so 2 pictures, that's the length of the nail. Now what I'm going to try to do, I'm not sure if I'm going to be able to do this or not, but I'm going to try to measure the width of the nail and still take a picture here. We'll see if I can do this or not. Yeah, we should be able to. I just got to finagle it a little bit and then see if it's positioned properly. Okay. So I've got it in the jaws of this these calipers, and now I'm going to take a picture or two. So what I'm measuring here is the diameter of the round portion of the nail. And I'll take 2 images as always. And that's all I need for that. A couple more measurements. I'm going to have to figure out what the diameter of the head is. And so I'm going to open this back up for a second and try to position the nail that way. I'm not sure if this is going to be the hard one, I think. So I'm going to lay this down, push this in. Of course, with our mass measurement being so crude, I don't think there's a whole lot of point of being careful, but I'm almost done with my measurements of the nail. We're looking at an alternative approach to water displacement. So I've got the head of the nail, my calipers this time. I'm going to go ahead and take a couple of images. I do need the diameter of the nail head so I can calculate the volume of just the head portion. So 2 images. And that should do it. Now, one last thing. I do need to measure the length of just the tip. So I've already gotten the length of the nail. I got the diameter of the nail head. And now I'm going to do just the tip of the nail. You didn't see me do this, but I positioned the nail head to such that I can measure the length of just the conical part of the tip head. I'm going to need that measurement as well. I already did that part with the ruler, but using the calipers, once again, is the more accurate thing to do to get that measurement. So 2 pictures of this. Now that's pretty much it for the dimensions of the nail that I'm going to need to calculate things. Now I'm going to move on to the last step, which is to measure the temperature of the water, and that'll wrap it up so we can calculate the specific gravity. One last measurement so we can calculate the specific gravity of the iron nail as well. We already have the densities, so this last measurement is a temperature reading. Now ideally I would have measured the temperature of the water, but unfortunately I stupidly dumped it out into a container. So I think the next best thing is the air temperature. And again, I think that's a fair assumption that the iron nail is the same temperature as the ambient air right now. So 2 pictures of this thermometer. It's laying down on the table. And we'll have all the measurements that we need to make a calculation with our mass, our volume, get the density, but also the specific gravity. In a video, I just showed you how to measure things. And so now let's look at the pictures that I took. And starting with the graduated cylinders, so I had this full of, well, not completely full of water, but a little bit of water. And the idea here is, since I'm after the density, I need to measure the volume of the object. And this is my starting volume of the water that I placed inside here. So obviously we always measure at the bottom of the meniscus, so I'm going to point this out with a little arrow here. So that's the bottom. See this lens shape right here that goes from here to here. Looking at this scale, I see 8 milliliters down here and 9 milliliters here, so I got to figure out what the graduations are worth. So 1, 2, 3, 4, 5. It looks like every graduation is worth a milliliter. So when I look at the meniscus, I see that it's at least 8.8 milliliters. I don't personally think it reached the 9 mark, so I think that the meniscus is slightly below that. So what I've done here is I've broken this little gap that you see here into tenths, mentally speaking. So it's at least 8, and I think it's about 8 tenths past this little hash mark. And so when it comes time to record the value, it's at least 8 milliliters. It's at least 8.8 milliliters. And this last digit right here is called the estimated digit. And it didn't quite reach the line, so I estimated it to be 8. Some people might call this a 9. Some people might call this a 7. Some people might even call this 8.90, and that's fine too. But this last digit is called estimated digit. Okay, it's because the meniscus does not fall perfectly on a line. I have to estimate it. And that's true for every measuring device. Always the last digit is going to be, except for electronic balances, of course, but you're going to estimate the last digit. Okay, so that's what I think it is. All right, so let's look at the final volume once I've dropped the nail inside here. So let me go ahead and clear the screen. So you see that the volume went up. That's a good sign because the nail does have volume. And again, I'm sure that it's at least 9 milliliters in this case, and it reached about the 9.19. So I don't think it reached 9.20 exactly. It's not perfectly on that hash mark, so 9.19. You may call it 9.20, that's fine, or 9.18, whatever. Now, because I have both the before I drop the nail in and after I drop the nail in volumes, the way you calculate the total volume, of course, is you're going to take these two values, and you will have to do this now at this point. You take the final volume, 9.19 milliliters, and the other value I think was 8.88. I hope that was the value that I got a second ago, and we're going to find the difference between these two. And this is called water displacement. So I'm going to calculate the volume of the nail because it displaced the water. So when I do this calculation, what I get is 0.31. And by the way, to do sig figs properly, I would drop a line down like so. But in this case, both numbers go 2 digits past the decimal point, so that's why this number is 0.31, and that's the proper number sig figs. So this is not a sig fig, by the way, it's 2 sig figs. That's despite the fact that there's 3 sig figs in here. Remember, the rules are different for difference and addition calculations. So anyways, 0.31 is the answer to the question of how much volume is in the nail. Now, I did some caliper measurements too, and that's actually the more complicated way to get the volume of the nail. So this is the way we would do this in the laboratory, is water displacement. So if you want to skip all this stuff with the calipers, go for it. You know, it's not that important, but still, nonetheless, it's important to see how I make measurements properly with something like a caliper or a ruler. Okay, so let's take a look at that now. Well, before that, I'm sorry. Here's the balance. So we have to get the mass, of course, too. And with the triple beam balance, what you would do is you would slide these weights over to the right until it balances out. Now, I just totally made up this measurement right here because this balance is broken, and I showed you that in the video, so don't take this too seriously. But this back weight right here, actually, let's start with the very back weight. This one's at 0, this one's at 0, so those are nothing. But this one I moved to 2, and that's 2 grams. And then I moved this tiny little slider over until it balanced out. And so it's at least 2 grams. It's at least 2.2 grams. And now what we do is we say it's 2.2, 1, 2, 3, 4, 5, 6, 7. I think it's at least 7. So 2.27. And then I'm going to estimate this gap from here to here. I'm going to break that mentally in the tenths. And I think it's about a tenth past this little hash mark, and that's why I'm calling it 2.271 grams. You might call this 2.270. Some people might call it 2.272, whatever. We're going to disagree a little bit, but that is what you have to do, is estimate that last digit. Okay, so this is called the estimated digit, and we're going to disagree a little bit. So this scale, if you do it carefully enough, is accurate to the nearest milligram, because if this is grams, 2 grams, this last digit right here is 1/1000th of a gram. So that's why we say to the nearest milligram, because you can get that accurate with this. I didn't give up on this, so I went to school later, went to Shasta College, and I put this on a digital scale, and it's 2.305 grams, and this is the value that we're going to use later in calculations. That's the most accurate. This is totally made up right here. This balance is broken. Funnily enough, though, I almost guessed the right value. I was pretty close to 2.305. That was just total coincidence, but anyways, that's how you read this scale. Okay, so this is an alternative approach to getting the volume of the nail. And like I said, you can skip all these measurements because it's not that important. But this is an alternative way because I can take the dimensions of the nail, including the length of it and the tip and also the head, and I'm going to show you, if you're interested, how to calculate the volume doing it that way. So it's a series. It's a bunch of different measurements of length is what it amounts to. So in this case, again, here's how you read this ruler. So you might want to watch this part. So this ruler is in centimeters, and I see that this nail head, or this length of the nail, goes at least to the 5 centimeter mark. And I need to estimate, I need to break this little gap right here into tenths, and how far past is this tip, past this little hash mark. So again, I'm going to call this, looks like I'm calling it 5.01, so 1/10 past this hash mark. It doesn't fall perfectly on the hash mark. What if it did fall perfectly on the hash mark? We would call this 5.00 centimeters. You do have to put that 0 there if you think it fell perfectly on the hash mark. So this ruler is accurate to the nearest 1/100th of a centimeter is the way to read this properly. And I will be looking for 3 sig figs in a situation like this. Now the head itself, I'm calling this the head down here. I'm estimating that to be 0.09 centimeters because I don't think the head is quite a full 0.1 centimeters, so 0.09 centimeters. I probably need that value later if you're going to watch that part. Okay, so calipers are even more accurate than rulers. And again, if you don't want to watch this part, just skip ahead. But what I did here is I've got the nail, the diameter of the nail is right in the jaws of this caliper. And luckily for me, I bought this a long time ago, and I bought it as a centimeter reading, and it's accurate to the nearest 1/10 of a millimeter is what it's telling us here. And so over here, let's start with this side first. I'm going to put this in red so you can see this. Over on this side, there's a scale over here that says 0 to 10. So what it says is since this little pointy thing here is less than 10, then we're less than 10 centimeters for our reading. In fact, we're way less than that. We're less than we're about 2 millimeters is what we're at. So less than what I mean to say is we're less than 10 millimeters. That's what I'm trying to spit out here. Okay, so since we're less than 10, then when you go to this little dial, these little numbers are in millimeters, as it turns out. So this is 1, 2. So this measurement is at least 2 millimeters, and it's at least 2.7 millimeters. And once again, I'm going to have to estimate this gap. I'm going to have to break it into tenths. And I think the needle is about 3/10 past this little hash mark right here. And that's why I'm calling it 2.73 millimeters. Converting that into centimeters, of course, I just moved the decimal point one spot, or I can say this, I can divide by 10. That's what we're doing. It's 0.273 centimeters. That's the diameter of this little nail right here. Okay. All right, so that's it for the diameter. Now there's a bunch more of these little caliper measurements. I'm going to go very quickly through these things because I think you'll get the gist of it after this one. So let's just go ahead and quickly do this. The next measurement was the length. So this is directly comparable to the ruler reading that I did not too long ago. And what I found was it was 50.58 millimeters. Notice that now this time we have to make sure that we pay attention to this little detail. It's at least 50 millimeters, and then it's about a little past 50 millimeters. So I said it's 50.58 or 5.058 centimeters. And that's pretty comparable to the ruler measurement that I did a second ago. All right, so here's the head, the diameter of the head. Again, in the calipers, I think it's 5.48 millimeters or 0.548 centimeters, whatever you want to call it. That's the head diameter. I'm going to need that to calculate the volume of this little head right here. The cone, you didn't see me do this, but the cone I put right next to these little pincers right here, and the length of the cone is about 5.32 millimeters is the way I read this. Okay, so that is the actual reading. You just don't see the nail here in this scenario. Okay, so last thing is temperature. So I've got a thermometer too that I took a look at. And the reason why I'm measuring the temperature is because by the time I get done with the actual density of the nail, I want to calculate the specific gravity, and I do need to know the temperature. Density is dependent on temperature, and that's why specific gravity is really convenient because it factors out temperature. So on this thermometer, again, it's important that you kind of look at the graduations and figure out what the graduations are worth. And on this thermometer, personally, I think that it's at least 20 degrees Celsius. Absolutely. Each hash mark represents a degree Celsius, so it's at least 21. And now, once again, I have to break this mentally into tenths. And I think this little fluid, this little red stuff, is about 2/10 past the hash mark. That's why I'm calling this 21.2 degrees Celsius. So this thermometer is accurate to the nearest tenth of degrees Celsius, as we say. Okay, so we just got done talking about measurements. So that was the raw measurements. I needed to pay attention to my significant figures. I needed to make sure that I grabbed all the digits that were significant for my measurements. Now, I said a number of times that the raw measurement that we just took, we just got done doing that, those should never be rounded in any way. Measurements, the raw measurement should never be rounded. By the time we actually start doing calculations involving measurements, though, the results of calculations have to be rounded, okay, not the actual measurements. And of course, with significant digits, all non-zero digits are significant in measurements, no question about that. Zeros in the middle part of a number are always significant. They are treated like any other non-zero digits. That's always true. Zeros in the front of a number, no matter where they're at, are never significant. So you see a zero in the front of a number, forget it. It's not significant. Now, the tricky one is zeros after the number and after the decimal point are always significant. Okay, it has to be after the decimal point, after the number, are significant. Zeros after the number, but before the decimal point, you can't figure out the number of sig figs for that, and you really have to use scientific notation to figure that out in that situation. There's no other way to do that. Okay, so these are our rules for sig figs. Let's again look at some examples and just quickly answer the question of how many sig figs do these numbers contain. And the starting one is 4 sig figs because the zeros in the middle part of the number are definitely significant. Now this one, zeros in front are never significant, so these are not significant. Only this one is, and so this is 3 sig figs total. This number, I did this on purpose. This one's, we can't determine how many sig figs in this one unless there was a decimal point here, but since there was no decimal point, you can't determine it. If I do put a decimal point here, though, that says that there's 4 sig figs. How do you show this number as 3 sig figs? You're forced to do scientific notation, so the only way to do that is to say 2.01 times 10 to the third is 3 sig figs. It's the same numerical value as 2010. How many sig figs is this? Zeros in the front are never significant, so there's only 1 sig fig for this. And this one, zeros after the decimal point and after the number. So what I mean is these are after this number, this non-zero digit, and after the decimal point. These are significant. There's 3 sig figs. Finally, these are zeros in the middle. Here's a zero after the decimal point, after the number. It's a grand total of 6 sig figs for this one. Okay, so I'm going to, after our sig figs discussion, I'm going to now start to take you through some calculation and show you how to use the calculator. In this first little exercise, we're going to go through scientific notation, just a quick calculation on our TI-84. If you don't quite have this virtual calculator that I have, TI-84, you'll probably have the simpler one, and it works the same way, so the buttons are the same. If you've got a Casio calculator, I'd be glad to show you how to do the scientific notation on that calculator too, but for now, here's the TI. So we're just going to multiply 2 numbers together. We're going to get a chance to enter this number on the calculator in scientific notation, check out how that works, and also round for sig figs properly. So here we go. So just multiply these 2 numbers together on the calculator, 1.234. And here's the scientific notation part. You hit the second button to access this secondary function, EE, and that takes the place of the times 10. All you have to do is enter the 3 and then times the other number, 0.54321, and then enter. And right away we get an answer. Let me just double check that I put this into the calculator correctly. It looks like I did. And we're ready to kind of give that answer with, let's see, 4 sig figs. So this has 4 sig figs. This has 5 sig figs. But of course, we're going to go with 4 sig figs, which is the correct way to do this. All right, so that's it. We've rounded properly. We've entered scientific notation. Let's just, for an extra little extra exercise, we're going to enter this number into the calculator using scientific notation. Let's do that. So on the calculator for this one, 670.3. Excuse me, I'm doing the wrong thing here. What I meant to do was to convert this first into scientific notation. So that means moving the decimal point 2 places, and this becomes 6.703 times 10 to the second in this case, since we moved it 2 places. And now let's try this again. We're just going to hit enter for this. So 6.703, and then the EE button again, second EE button 2. And if we hit that, we of course get the same value back. Okay, so that's working with scientific notation. That's rounding for sig figs properly. Now we're ready to get back to that nail experiment that I was already talking about, where I measured some values, and we're going to get a chance to calculate the density at this point. So let's take a look at the next calculation. I'm going to clear the screen real quick. Oops, that's not what I wanted to do. Clear the screen. So we measured the volume of an iron nail. The initial volume of water in the grad cylinder was 8.88, and the final volume was 9.19. We've already done this calculation, but it's worthwhile to do it again. So we need to find the difference in the volumes for that water in the cylinder. This is called water displacement. And we take 9.19 milliliters and then 8.88. We're lining these numbers up on the decimal point for proper sig figs, because we're going to drop a line right there, and that's going to tell us where to round, and that's a difference calculation. So let me just do this really quickly. So this is 1.1130, and there's no digits right here, so that's the easy part. But nonetheless, this is 2 sig figs, despite the fact that we started with 3 sig figs. Remember, the rules are different for difference calculations, and that's it. So that's the volume of the nail that as we determined by the graduated cylinder. Now, this next calculation is an alternative method for getting the volume of a nail. You can skip this next section. I think it's going to take about a couple of minutes, maybe 5 minutes to get through it. It's a more advanced way of getting the volume of the nail. The simplest procedure is just what we did, is the grad cylinder experiment. So just skip the next section if you want to. So let's take a look at that now and see how that works. So this is method 2 for getting the volume of a nail. This one's a lot more tedious, so if you don't want to watch this, skip it, because the more important method is graduated cylinder water displacement. Now what I've done is I've taken the nail and I've broken it down into essentially 3 pieces. So one is the length of the nail. That's something we treat as a cylinder. The tip we treat as a cone, and then the nail head we treat as a cylinder once again. So here's all my measurements, except for I forgot to write down one of them. This was 0.09 centimeters for let's see, that was the thickness of the head is what it was. All right, so starting from the top, the first thing that I did is I calculated the volume of the shaft. So that's from this point to this point, not including the tip. And we've got pi. So the equation down here, this is the volume of a cylinder down here. So pi times the radius squared. This is the diameter. So the diameter, if we have that, becomes the radius squared. And then finally times 4.526 centimeters. The volume of the tip we treat as a cone. The cone formula is down here, pi r squared, height divided by 3. So here's pi, here's the radius squared, and then the length of the tip is like the height, and so that's why I have this value in here, 0.532 divided by 3. And then finally the volume of the head is pi times the radius squared times the thickness, 0.09. So this is a cylinder again. So I've got 3 separate volume values, and I got to finally add them together. And I've got all these things pre-calculated. I didn't want to waste time in this video doing this, but entered them into the calculator, 0.265, 0.010, 0.021, and with sig figs in mind, I'm going to round this way. So 0.296, finally cubic centimeters, and that compares pretty well to the grad cylinder method that I got before. So either way. Now I do want to show you how to enter one of these values or one of these calculations into the calculator just for a little more practice. Let's do this top one, which is pi, and then the diameter times, excuse me, divided by 2 squared times this. On the calculator, you can access pi by saying second pi, so that's really convenient. Then times. Don't be afraid to use parentheses. You can never have enough parentheses, so 273 divided by 2. The way we do power on the calculator is caret. I call this the caret key, and we need to square this, and then times 4.526 and enter. And of course, that's the 0.265 that we had before. That's this value right here. And eventually I went on to calculate this one, try those if you want to. And I've got all 3 values lined up on the decimal point. I add them together, it's 0.296. All right, so that's all I want to say about this calculation. This is a second method for calculating the volume of a nail. This one's a lot more tedious, probably less accurate too, versus the grad cylinder method. Okay, so let's move on. Let's take a look at something else now. Here we go. I had to advance the slide. Let's calculate the density of an iron nail finally. So I've got the mass of the iron nail. I just a second ago calculated the volume using a couple different methods. Now finally, let's do this. We're going to get that density, and density of the iron nail is density. And then the mass of the nail is right here. I've got it, 2.305 grams. And we'll just go ahead and use the previous volume from the second method. I could use the grad cylinder one too, which is a little bit different, but that's fine. So cubic centimeter is the same thing as a milliliter, so we're just going to go ahead and say milliliter. And that's typical what density units are in. So on the calculator, once again, I'm going to go to my calculator, clear this, and then 2.305 divided by 296. Okay, so that is about the density of iron, so that's good. So with sig figs in mind, we've got 3 sig figs to work with, so 7.9 grams per milliliter. Okay, so that's it for our iron nail exercise. I think we made this way harder than it was supposed to be, but I just wanted to take you through some measurements and show you how to work with calculations, the calculator, scientific notation, all that kind of stuff. I've got some more practice problems coming up, and so let's take a look at some more things. So let's go ahead and advance here, if I can. Let's calculate the density, or the specific density. I forgot, I'm not quite done yet with the iron nail. So we just got the density a second ago. It was 7.79. Before we move on, we're going to calculate the so-called specific gravity. This is mislabeled here. This should say specific gravity of an iron nail. And for that, I measured the temperature of the water. I showed you that as well. It was 21.2 degrees Celsius. And at that temperature, water's density, I looked this up online, it's 0.99795. So the way we calculate the specific gravity is we just take that previously calculated value, which was 7.79 grams per milliliter is what we had. And water at the same temperature as the iron, 0.99795, same units. And that's why by the time we do this division, we're going to see that there are no units on specific gravity. Okay, so once again, we have to pay attention to sig figs. So this is going to be 7.81. There are no units because they cancel out, so grams per milliliter over grams per milliliter. So the value I expected this, it's going to be very similar to the original density because water's density is still almost 1 at that temperature, but nonetheless, that's called the specific gravity. It's a very easy calculation as long as we can find water's density at the same temperature. Okay, so some more practice problems. This one's a little bit easier than what we were working on before. Let's take a look at some unit conversions. So let's convert between kilos, centi, milli, micro, nano. I've always got questions like this. So 1.1 kilometers is blank meters. Now the kilometer is much bigger than a meter, so I expect that the number of meters is going to be a fairly large number because this is a large unit right here. And this is a fairly straightforward calculation. I'm going to give you the conversion factor, and that conversion factor is that there's 1 kilometer for every 1,000 meters. I'm not going to calculate this just yet. I'm going to finish all the setups first and then calculate. So this next question, we're starting with 10.00 kiloliters, but this time we're going to milliliters, and what I suggest that when you're first learning this is to say 1 kiloliter is 1,000 liters. I'm taking this to what I call the base unit being liters. And then from the base unit, I'm going to say 1 liter is 1,000 milliliters. And we'll calculate that in just a second. So everything cancels properly. I'm left with milliliters. And then finally, 0.0100 centigrams. We don't deal with that unit very often. This one, well, we'll still do it the long way. So we'll say that we'll say this, 100 centigrams is 1 gram, and 1 gram is 1,000 milligrams. Okay, so now I don't think I need to put this on the calculator because I can see what's going to happen already. So in this calculation, I'm just going to directly put this into scientific notation. 1.1 times 10 to the third meters is the answer to this one. And that's the correct number of sig figs because this is 2 sig figs. This one doesn't count as it's an exact quantity. Now down here, this is 10.00. So what I'm going to do is I'm going to go ahead and convert this into scientific notation directly. And what I need to do is make sure that with 4 sig figs here, this front part of this scientific notation is also 4 sig figs. And then I've got 3 and 3, which is 10 to the 6, but I already moved the decimal point 1, so that's 10 to the 7. And then that's going to be kiloliters. Excuse me, it's not going to be kiloliters. It's going to be, let me erase that, it's going to be milliliters. That's what we converted to. So that makes sense because 10 kiloliters is already a lot, and milliliters are smaller, so we expect a very large number when we do this. Now this last one, I could probably do this without the calculator too. This is 1,000 divided by 100. That's 10. So all I have to do is move the decimal point 1 place. But I need to keep those 2 digits, those 2 zeros at the end here. But it is now milligrams at this point. Okay. All right, so that's it for some basic conversions. Again, I suggest that you learn how to do this the long way, where you take it to the base unit and then from the base unit to our final destination. All right, so let's clear this now. Let's take a look at something else. More dimensional analysis. So what is the mass in grams of 0.231 liters of iron if the density of iron is 7.874 grams per milliliter? Show all the work. So this one should be pretty straightforward. What is the mass? What is the mass? So I've got 2 values, and the only value that gives me a mass is this second one, which is the density. I'm going to start there. And that's grams per milliliter. I can't just multiply it by liters without, first of all, converting milliliters into liters. But then now finally I can multiply by 0.231. And all the units are going to cancel properly. I'm going to be left with what I want. I don't think I can do this one in my mind this time, so I'm going to try to do this on the calculator. So 7.874 times 1,000 times 0.231. Okay, so back to here. We've got 3 sig figs to work with, so now we're looking at 1.82. The only way to do this properly is to use scientific notation. So this is going to be to the 3rd power, and that's going to be grams. Okay, so what is the mass in grams of this volume with this density? That's the answer right there. That's the setup. Okay, so this question looks almost the same as the previous. In fact, it barely changed from the previous slide to this one, but this time I'm saying 0.231 kilograms, so this time I'm specifying the mass, and we're doing the opposite. We're getting the volume. So let's try this. We are going to get a different value this time. Now the kilogram, looking ahead to the grams, I see that I'm going to have to convert this right away into grams. And then finally, if I just multiply by the density, I'm going to almost get, I made a mistake. I can see what I did already. So I didn't flip this. This has got to be flipped upside down. And that was the whole point of this question, is to say that this density value, the beauty of dimensional analysis is I can flip these numbers however I want to. So I got to keep the units the same though. So this is still grams, but it's got to go to the bottom, and then the milliliters goes to the top. There we go. That's the correct way to do this, because now kilogram, kilogram, gram, and gram cancels. And I'm going to be left with hopefully what I want here. So let's see. All right, so times 1,000. And then divided by 7.874. Okay, so we're looking at a volume with, once again, 3 sig figs, so 29.3 milliliters this time. Okay, so that's it. Just more dimensional analysis. Let's see what else we have. I got lots of practice problems here. How much did it cost you to drive 310 miles to Sacramento and back if the cost of gasoline is $2.59 per gallon, which is about right for right now as of spring 2015, if your car gets 28 miles per gallon? Okay, so the question is, how much did it cost you? So I'm already looking at this value right here because that's the one that has cost. I really want to start with the $2.59 because in the end I want dollars. And this slash, again, just keep that the same, so that's per 1 gallon. And I drove, well, let's see, what else can we use here? So 28 miles per gallon. Remember, 28 miles per gallon is the same thing as 28 miles and then slash gallon. And with that value, I see that I need to put the 1 gallon on top here and then 28 miles on the bottom. So I'm free to flip this value upside down. I have to because I want the gallons to cancel with gallons. So I've solved the gallon problem, but I created a new one with the miles. But I did see that I drove 310 miles. I think that's the last thing that I do is 310 with a decimal point miles. By putting the decimal point, that indicates that it's 3 sig figs. And now I just simply put this onto the calculator. I think we're ready to go. Okay, so we're looking at, well, this issue came up in lecture. You know, it's kind of one of these sticky little issues that, you know, dollars should be really rounded to the nearest cent. But I'm going to go ahead and just use the scientific approach by saying that this is 3 sig figs, 3 sig figs, 3 sig figs. This is going to be 28.7, and that's dollars. Okay. Now, if you're not sure what you want me to, what I want you to do, ask me during the test, and I'll tell you exactly how to round this. Dollars and currency represent a real challenge sometimes for sig figs, so it's hard to know what to do. Okay, so that's just another example of dimensional analysis. Let's see what else I have. I think I have still some more. All right, so finally, I'm not ready to do this problem yet because I've got a short video to show you before I do this calculation that really shows you exactly what we're going to do in this little calculation. So let me have you take a look at the measurements of the mass of the iron pan, the temperature change, and we'll calculate the heat in just a second. So stay tuned. Hello and welcome to my kitchen. I'm going to show you a quick demonstration of how the specific heat calculation works. So I've got a cast iron pan that I really like to use when I'm cooking on the stove right now, and I also have this little thermal sensor. This works with infrared, so all I have to do is point this towards the cast iron, and what I'm going to do is I'm going to get an initial temperature of this cast iron pan. It looks like it's telling me 23.9. If you don't believe me, I'm going to bring this closer here. Sorry, I'm going to aim it. So 24, actually it's 24.1 before I start heating this cast iron. So cast iron, of course, is made out of iron, and it's really cool stuff to cook with for a lot of reasons that I don't want to get into, but I've got an initial temperature about room temperature. Now, just to prove my point, I'm going to go ahead and take this cast iron off the stove and turn on the burner at this point. Okay, so I've got that on. Now, of course, combustion of natural gas is providing the energy that we need to heat up the cast iron, so we hope that most of that energy that's being produced in combustion is going into the cast iron pan. So the iron is absorbing all this heat. So I'm going to go ahead and just put this on. And I'm going to let this go for about 2 minutes or so. And then I'm going to take the final temperature, and eventually what I'm going to do for you is calculate how much heat was absorbed by this cast iron pan. What I'm going to know in terms of variables is I'm going to know, first of all, the initial temperature, and then eventually I'm going to get the final temperature, and then I already know what the specific heat is of iron. I looked it up online. I'm going to be able to calculate how many calories of energy went into this cast iron pan. So I'm not going to wait too long. I'm not going to keep you hanging here, but after a couple of minutes, I'm going to take the final temperature. Now, a couple of assumptions that I make about this process is that I assume that the heat that's being produced is completely absorbed by the cast iron pan. That's a pretty gross assumption. A lot of it's leaking out the side, but that's fine. It won't affect our calculations too much. The other gross assumption that I'm making is that the iron is completely distributing the energy, and that's probably not such a great statement either, because the heat, most of it's concentrated in the middle part of the pan. I doubt that the handle is going to be nearly as hot as the surface itself, but that's okay. This will still work for an analogy. All right, so I think at this point I'm done heating it, so I'm going to go ahead and take the final temperature once I turn off the stove. Let me go ahead and do that. Okay, so now the final temperature. I expected it to be a lot hotter than this. It didn't go up too much, but so I'm going to go ahead and just call it right here. So if you can see that, it says 133.2. That's the final temperature. I'm going to need that value. The other thing I'm going to need before I'm done with this experiment is I'm going to need to know the total mass of this pan, and that I'm just going to weigh it on a bathroom scale and see what I get, and I'll convert it to mass in just a second. Okay, so let's go ahead and take a look at the calculations, see how we calculate the heat absorbed by this pan. Okay, you didn't see me do this, but I put the cast iron pan on a little bathroom scale. Unfortunately, I'd wanted to use my digital scale, but the pan is just simply not heavy enough, ironically, to register something on the scale, and that digital scale reads kilograms, so I'm going to have to do it the good old-fashioned way. And I'm going to get a little bit closer so I can see what's going on here. It's at least 5 pounds as I see it, so I'm going to have to look at the video later and see exactly what it was. But this scale looks like the hash marks are to the nearest pound, and I'm going to have to estimate to the nearest tenth of a pound later as I start to look at the footage. But this is me weighing the pan in pounds. I'm going to have to convert to kilograms and then grams later. I took you through the actual measurements of that cast iron pan now, and the relevant equation that you'll have available to you on the test is heat equals the mass of the object. Most of the time we're dealing with water, but not so this time. We're dealing with the cast iron pan times the so-called specific heat. So I'm just going to leave this as a generic C for now. C is the official symbol for specific heat. And then finally times the change in temperature. So the final temperature always subtract the initial temperature, and that's the calculation we want here. Also, I measured I measured the mass in pounds instead of grams because that's the only thing I could do. So we have to take that into consideration too. So here we go. So heat equals, let's see. So I found the mass to be 6.8 pounds. That's what I have to start with. And right away I'm going to have to convert that. So 1 pound is 453.59 grams. Okay, so if I stop right there, I'd have grams. That's what I needed. So pounds and pounds cancel grams. And now times, I looked up previously the specific heat for iron. It's not the same as water. So water is 1 calorie. This is 0.108 calories per 1 gram per 1 degree Celsius. Now remember, the specific heat is the amount of energy in calories to raise 1 gram of iron by 1 degree Celsius, and that's the value. You can find this pretty easily online if you Google it, and then times the temperature change. So the final temperature was 133.2, and the initial was 24.1, which is about room temperature. Okay, so on the calculator, I need to do this little pre-calculation first because the rules are different for sig figs here. And so on the calculator, 133.2 minus 24.1. Okay, so just to make sure my sig figs are right, I'm going to line up these two numbers on the decimal point. These are both in degrees Celsius. And my calculator, well, before I do that, I'm going to drop this line, and the calculator says 109.1 degrees Celsius. And that is the proper number of sig figs for this. Remember, the rules are different. Despite the fact that this is 3 sig figs, we drop that line, we get 4 sig figs this time. So now equals, now I just have to simply put this onto the calculator. All right, so 6.8 times So that's a really heavy pan. It's made out of iron. And then times 0.108 times 109.1. Okay, so I'm forced to put this into scientific notation because I'm limited to 3 sig figs, it looks like. And in scientific notation, this is 3.63 times 10 to the 1, 2, 3, 4. It looks like the fourth. That's a lot of calories. That's little c calories, okay? So if I want to convert this into nutritional calculators, I just simply divide by 1,000, and that takes me to nutritional calculators. I don't think I'm going to do that. We'll just leave this as little c calories. And so that's the amount of energy that I got to put into that pan to raise the temperature from 24.1 to this. So that was turning on the stove in my little demo. All right, so I think that's that's it for the sample calculations. I think that's it for part 1 in the review. I've done quite a few calculations, and there's still part 2 to go. So in part 2, I'm going to be looking at electron configurations, atomic theory, and that kind of stuff. So that'll come hopefully by the exam next week.